Okay, so last time we talked about this idea of thermal resistances and how thermal resistances are useful because they do a couple things. One is they let you put all these different kinds of heat transfer mechanisms onto the same sort of footing so that you can develop models that have a bunch of things going on. And then actually, probably more importantly, they let you compare these different processes so you can understand what's important and what's not important. So I thought today we would do an example actually of a problem that we can solve using thermal resistances. So here's the problem that I came up with. This is a power electronics chip. This is maybe something you would find in a high-speed switching motor, so this could be the controller for that. So what this chip would do is take in current and basically just switch it on and off in order to run a motor. So maybe some kind of PWM type motor. And these switches are not 100% efficient, and as a result, there will be some generation of thermal energy in the power electronics themselves, and the power electronics then have to be kept cool, right? So that's a challenge with these kind of devices. So this square is the silicon chip, right? It's 1 centimeter by 1 centimeter. We're looking at it from the top. If you look at it from the side, you can see that the thickness of the chip is 3.2 millimeters, and the chip is actually pretty high conductivity. Silicon's pretty high conductivity, so 121 watts per meter Kelvin. And then this is actually where the thermal energy is generated. It's generated inside of this silicon, not actually uniformly, so it's preferentially generated towards the top where the operations are happening, and we're going to approximate that thermal energy generation as being 5 watts at this surface right here. So 5 watts is introduced at this surface right here, and that's what's causing the chip to heat up, right? So that's an approximation, but a reasonably good approximation. Okay, so what else is going on? The chip can be, it has to be cooled, so it can be cooled from its top surface, right? Because it's exposed to air and also some radiation. So this surface has an emissivity of 0.9. It's surrounded by air at 30 degrees Celsius, and the heat transfer coefficient between the surface and the air is 37.2 watts per meter squared Kelvin. The chip is also cooled by mounting it onto a thermal management system, right? So you mount the chip onto this larger spreader. The spreader is made of some kind of material with a relatively high conductivity, so that's what this is. If you look at the spreader from the top, you can see that it's got a larger cross section, so it's 2 centimeters by 2 centimeters with a 1 centimeter by 1 centimeter chip located on it. The spreader thickness is 7.5 millimeters, and the spreader has a high conductivity of 85 watts per meter Kelvin. The spreader is usually conductive. It's some kind of metal, and so you can't just paste an electronic chip to a piece of metal. You have to electrically isolate the chip, so that's what this dielectric layer is. The dielectric sits between the chip and the metal. You make it as thin as possible, so here 0.35 millimeters, and the reason you do that is because it's hard to find a dielectric that is thermally conductive, so usually these things have fairly low conductivity. This one has 0.85 watts per meter Kelvin. And then the spreader is cooled somehow, usually on the surface down here. We're going to assume water cooling down here, so you have a heat transfer coefficient that's pretty high for water, and the water is at 20 degrees Celsius. So that's the situation, right? And I guess in the end what I'd like to know is, how hot does this get? How hot does my chip get? Do I have to worry about it malfunctioning, or at least the performance being degraded, the lifetime being degraded because it's too hot? Also, maybe even as important as that is, what can I do to keep it cool, right? What part of this thermal management strategy is the most important, and which parts are just basically not important at all? So we can attack this problem, at least initially, using a thermal resistance network, and that's what we've done over here. Right, so this thermal resistance network if I start at the spot where I'm putting the energy in, then basically the thermal resistances represent the path that the energy can take, right? So here, this is the node that represents the top of this chip, right? And that's where the 5 watts enters. And you can see the 5 watts kind of has a choice, right? Some of it can go to the air and the surroundings, and that happens by radiation and convection. So that's what I have going this direction. I have convection to the air, and I have radiation to the air, and that gets me to T air. Some of that 5 watts can go down, right? And so that's going through the chip. That's what this conduction resistance is. Through the dielectric, that's what this conduction resistance is, and then through the spreader, and finally convected to the water. So we're neglecting, I guess, contact resistance for this particular problem, but we have a whole bunch of other things going on, and that's the idea. That's what we have to simulate. We're going to simulate this in ease. So let me show you the ease file here, if I can bring that up. So the first thing I did here in ease is put in all of the inputs, right? So all this stuff up here is actually just inputs from the situation, right? The problem statement. And if you've never used ease before, again, there are tutorials on the website that you can use to get yourself started, but one of the most important and most attractive features of ease is that it will keep track of your units for you, right? So you'll notice that when I put these inputs in, I didn't just put in that the chip width is 1 centimeters. I also converted that centimeters to meters. So the chip width now is in meters, as is every other input to the problem, right? And the reason I'm doing that is because I personally like to work in all base SI units so that I don't have to worry about units getting screwed up as I'm moving through the problem. All right, so that's the inputs here. The next thing I have to do here is actually calculate the resistances, right? So I know this temperature, I know this temperature, I know how much heat I'm putting into the circuit. I could solve the circuit if I was given all of these resistance values, but of course I'm not. I have to calculate them. So let's sort of go through these one by one and knock them off as I do them. So let's start with our conduction for the chip. This is, at least we're going to simulate this as being conduction through a plane wall, right? So conduction through a plane wall, we said the resistance is how far do I have to conduct. So I have to conduct across the thickness of the chip. That's how far I have to move the energy, divided by the conductivity of the chip, and then the area available for conduction. So the area available for conduction is the area that I see when I look down on top of this chip, right? So our conduction is right here. It's the thickness divided by WC squared times KC. And here's a suggestion I'm going to make if you're using ease or really any computer tool. I'm not going to continue until I enter this equation and check it and make sure it looks right? I'm gonna go through this as sequentially as I can, so that I'm not making a whole bunch of mistakes and then trying to fix them at the end. I'm making my mistakes as I go, right? Which is actually kind of an important thing for debugging. So that's what I did here, right? I would enter that equation that I just derived. I put it in. I'd solve it, right? I would make sure that our conduction chip has the right units, and that if I check the units, I don't get an error. So everything seems good before I go to the next equation and enter it, and then the next equation and enter that. And what that does for me then is, if I do run into problems like this equation won't solve, I know exactly where the problem was. It was in the last equation that I entered, because before that everything worked fine, and after that everything didn't, right? So that's a kind of an important lesson to learn whenever you're using computer programs. All right, so this one is fine. I know everything over here. I can solve this equation. Do the same thing for the conduction through the dielectric. So that's the conduction across this layer right here. Conduction through the spreader. So here I have this thickness, and then the area of the spreader is the WS times WS. And then finally convection from the water, right? So that is 1 over this heat transfer coefficient, and then the area exposed to the water is WS squared. So I have all these 4 done. Now I come over here, convection to the air. So convection to the air is convection from this surface. So 1 over this surface area is WC squared, that surface area, times H bar A. And at that point, everything seems to be working, right? I can calculate those 5 resistances without any problem. I have 1 resistance left to go, which is R radiation. So let's look at that. I can go to the next slide. It'd be awesome. So R radiation is calculated according to this equation here that we derived, right? And if you remember what this equation was, it's 1 over the emissivity of the surface, right? So we know the emissivity. This sigma is Stefan-Boltzmann's constant. That's easy. It's a built-in constant in ease. This is the area doing the radiation, right? So the area doing the radiating, this is WC squared. And then I have the surface temperature plus the surrounding temperature, and then the surface temperature squared plus the surrounding temperature squared. So everything in this side of the equation I know, except I don't actually know the chip temperature, right? That's the whole point of this problem, is I'd like to predict this chip temperature right here. So if I enter this equation and I hit solve, ease is going to tell me you can't, right? You can't solve this equation because you've entered 1 more equation, but you've entered 2 more unknowns, and so I don't have enough unknowns and equations anymore. So, you know, I just won't be able to solve the problem. And so at this point, there's kind of 2 choices that you have. Choice number 1 is you continue to add equations, hoping that eventually you'll get to a point when you hit solve, you have enough equations and enough unknowns. And that's not the best choice, I would say. The best choice at this point is to do what I would call a guess, and then eventually close up your guesses, right? So if I were to make a guess for what this chip temperature was, it doesn't have to be right or even very good. It would let me calculate this resistance, right? And if I can calculate this resistance, I can check that equation, and then I can continue going through the problem, always remembering that eventually I better be able to solve for that chip temperature that I initially guessed, right? And then I'll be done. And this is a pretty simple problem, but you'll find as the problems get more complicated, this is a pretty important skill, right? You really want to be able to continue to sequentially solve your problem as you move through, in order to do this in a systematic manner that's easy to debug. So that's what I'm going to do here, right? I am going to, in ease, make a guess as to the chip temperature. I just said, you know, let's guess that the chip temperature is the air temperature, so 30 degrees Celsius. Obviously, I know that's not right. I'm going to highlight it so that I don't forget that, you know, if I haven't gotten rid of this guess, my problem is still incomplete, right? But with the guess, then I can add this equation for R radiation and actually solve at this point and get a value, right? And I can check it and make sure everything works. So that's nice. At that point, then I would have every one of these resistances either calculated or estimated, right? And then I can move forward and actually try to solve my network. So let's see how this works. This is something you should have learned in circuits. What do I have going on here? If I do an energy balance on this node right here, I have coming into it obviously the 5 watts, and then I have leaving it whatever goes from here to the water, and then whatever goes from here to the air, right? So what goes from here to the water is TC minus TW divided by the sum of these resistances that are in series. So this is what's coming in, this is what's leaving right here to the water, and then whatever goes from here to the air is TC minus T air divided by these 2 resistances are in parallel. So TC minus T air, and then this is the parallel combination of those 2 resistances. Remember, if you want to combine resistances in parallel, what do? You take 1 over each resistance, add them together, and then when you're done, you take the inverse of that, right? So I took 1 over each of these 2 resistances, added them together, and then took the inverse of that. And this would still hold if I had 3 or 4 or 5 of them. I'd just be adding more and more inverses. Okay, so I can enter this equation, right? I have 5 watts, I know the water temperature, I know the air temperature, I know all these resistances, and it will allow me to calculate the chip temperature, right? So at this point, you know, I earlier guessed what the chip temperature is. This is actually going to let me calculate the chip temperature, right? So that's what I'm going to do here, is I will calculate the chip temperature. Right up here I guessed the chip temperature, that's why the little g is here. Here I'm going to calculate the chip temperature. So my guess for the chip temperature was 303.2. according to my calculation, it's actually more like 341.7. So obviously I'm not done yet, right? These two numbers have to be the same. At this point, if you were of a certain age, like me, you would iterate, right? So what that means is you would come back here, you take this chip temperature, you go back up here and redo your calculations using it as a guess, and you would hope that eventually your chip temperature stops changing, right? Ease makes this much easier to do, and the way you do this in ease is you say, I'm going to now add another equation, and that equation is going to say I need the guess chip temperature to be equal to the actual chip temperature, right? And then that's going to be one too many equations, so I'll take out this, which wasn't right anyway, and I'll hit solve, and hopefully it'll solve, right? And the hopefully part stems from the fact that ease is an iterative equation solver, and it starts from a set of initial guess values, and it tries to make those guess values better and better and better, right? Just like you probably learned in some math classes when you learned Newton's technique for finding solutions to sets of equations. That's all ease is doing, albeit a little bit more sophisticated way. So my point to that is every one of these variables has a guess value, right? And ease starts from that set of guess values and then tries to converge to the right solution. So if these guess values are not very close to the right solution, there's a very good likelihood you're never going to get to the right solution. You're going to converge to the wrong solution, or maybe you won't converge at all, right? So one of the things that you can do at this point, and one of the reasons why this is such a nice way of doing the problem, is before I comment out this equation, I'm actually going to come up here and hit this little G button, or I guess if I go to calculate, I can hit the update guesses menu item here. And all that does is it says, I don't have the right answers right now, but I have answers that are pretty realistic. They're in the right order of magnitude. So rather than starting from some arbitrary set of guess values, let's start from whatever the values are right now, right? And that's what this G button does. It sets the guess values of all the variables to the most recent calculated values, right? That's what it says. And we'll hit yes, that's what we want to do. And then I'll come in here and I'll say, okay, now I want to get rid of that equation, and instead I want to require that the guessed chip temperature and the actual chip temperature are the same, and we'll hit solve. And because I update my guess values, I don't have any troubles, and it finds out that the guess temperature is 341.6, and that's equal to the actual chip temperature now, 341.6, right? So we actually just did something fairly complicated, and that was we solved a big set of coupled equations, right? And the reason that it worked without a hitch is that we started that solution process from a reasonable set of guess values and let it converge to the right solution. And that's a very useful trick when you're using ease. It's not even a trick, it's just a useful technique that you should get used to doing whenever you're using ease.